What if a visitor from another star system is doing something to our sun that we've never witnessed before? What if right now, as you watch this video, an object is interacting with our solar system's heart in ways that challenge everything we thought we knew about comets, solar dynamics, and the delicate balance that keeps our planet habitable? Tonight, we venture into territory where astronomical curiosity collides with cosmic dread, where the predictable dance of celestial mechanics crumbles, and an unsettling possibility takes root. That 3I Atlas, a comet from the depths of interstellar space, isn't behaving like anything we've catalogued in 4 centuries of astronomical observation. The sun doesn't change, not really. Not in ways that matter to us over human timescales. It's been our constant companion for 4.6 billion years, a nuclear furnace so reliable that civilizations have measured their existence by its daily return. We understand its moods, its 11-year cycles, its coronal mass ejections. We've sent spacecraft to taste its outer atmosphere. We've mapped its magnetic field lines with exquisite precision. And then came 3I Atlas. On December 2nd, this interstellar wanderer will make its closest approach to our Sun, diving to within 0.039 astronomical units of its surface. That's roughly 3.6 million miles, or just over 5.8 million kilometers. To put that in perspective, it's getting closer to our Sun than Mercury ever does. It's plunging into a region where temperatures exceed 1 million degrees Celsius, where solar wind screams outward at 450 kilometers per second, where the very fabric of space is twisted by magnetic forces powerful enough to hurl billion-ton clouds of plasma toward Earth. What happens when an object from another solar system, formed in conditions we can barely imagine around a star whose light we may never identify, enters this hellish domain? The official position is measured and calm. NASA assures us there's no threat to Earth. The European Space Agency has characterized 3I Atlas as just another comet, albeit one with an unusual trajectory. Scientists speak in careful language about observational opportunities and unique spectroscopic windows. The message is clear: stay calm, this is fascinating but not frightening. But what if they're watching something unprecedented? What if instruments are detecting interactions between this interstellar visitor and our Sun that don't fit the models? What if 3I Atlas is doing something to the solar magnetic field, to the coronal structure, to the delicate balance of forces that govern space weather throughout our solar system? Comets have grazed the Sun before. We call them sun grazers, and we've documented thousands of them, mostly through the SOHO spacecraft's tireless vigil. The vast majority are members of the Kreutz family, fragments of a massive comet that shattered centuries ago following predictable orbits, behaving in predictable ways. They vaporize spectacularly. They contribute water and organic molecules to the solar corona. They're beautiful, ephemeral, and utterly unthreatening. 3I Atlas is not a Kreutz comet. It's not part of any family we recognize. Its trajectory didn't originate in our Oort cloud or Kuiper belt. It came from the space between stars, carrying with it the chemical signature of another solar system, another stellar nursery, conditions and compositions that might differ radically from anything native to our cosmic neighborhood. And now it's about to kiss our Sun. What if its alien chemistry reacts differently with solar plasma? What if its magnetic field, shaped by exposure to interstellar radiation for millions or billions of years, couples with the Sun's magnetosphere in ways our models never anticipated? What if it triggers a cascade of solar activity that sends a coronal mass ejection screaming toward Earth with timing and intensity we can't predict? What if the terrifying part isn't what might happen to Earth, but what we might learn about the true nature of our Sun, that it's not the stable, predictable engine we've always believed it to be, but a complex, reactive system that can be influenced, perturbed, perhaps even wounded by the right visitor from the cosmic depths? Before we dive deeper into this unprecedented story, If you're intrigued by cosmic mysteries and solar science, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is where you're watching from and where you're located. I love seeing our global community come together to explore these astronomical questions. And if you appreciate the research that goes into these deep dives, a like really helps the channel grow. Now let's continue into the strange saga of 3i Atlas and what it might be doing to our sun. Let's address the elephant in the room immediately, because I know what you're thinking. If something is doing something terrifying to our sun, and we depend on the sun for literally everything, our warmth, our food, the very existence of liquid water and breathable atmosphere, then shouldn't we be concerned? Shouldn't there be emergency broadcasts? Shouldn't we be heading for bunkers? The short answer is no. The official position from every credible space agency on Earth is unambiguous. 3i Atlas poses no direct threat to our planet. Discovered on April 27, 2024, by the Atlas Survey System in Hawaii, the same system that gave the comet its designation, 3i Atlas was immediately flagged for its hyperbolic trajectory. Unlike the vast majority of comets that orbit the Sun in elliptical paths returning periodically to the inner solar system, 3i Atlas is on a one-way trip. It came from interstellar space, and after its solar encounter, it will return to interstellar space, never to be seen again from Earth. NASA's Jet Propulsion Laboratory has calculated its orbit with remarkable precision. At closest approach on December 2, 2024, it will pass 0.039 AU from the Sun's center. That's inside Mercury's orbit, but still more than 3.6 million miles from the solar surface. For context, the Sun's radius is about 432,000 miles, so 3i Atlas will pass roughly 8 solar radii from the Sun's surface, close in astronomical terms, but not a collision course. More importantly for Earth's safety, 3i Atlas never approaches our planet closely. Even at its nearest point to Earth, it will be over 130 million miles away, farther than the Sun itself. There is zero chance of impact. There is zero chance of its gravitational field affecting our orbit or rotation. There is zero chance of debris from its tail reaching Earth's atmosphere in any meaningful quantity. The European Space Agency's Near-Earth Object Coordination Center has given 3i Atlas a Torino scale rating of 0, meaning no hazard. For reference, the Torino scale runs from 0 to 10, with 10 representing a certain collision capable of causing global catastrophe. Objects are regularly discovered that briefly rate 1 or 2 on this scale before refined observations reveal they'll miss Earth. 3i Atlas never even reached 1. So if the physical threat is non-existent, why the ominous title? Why the suggestion that something terrifying is happening? Because the real story of 3i Atlas isn't about kinetic energy or collision dynamics. It's about what this interstellar visitor might be revealing about the Sun's behavior, about solar comet interactions we've never observed before, and about the delicate, complex, and potentially more variable nature of our star than we've previously understood. The Sun is not a passive backdrop against which comets perform. It's an active, dynamic system with its own moods and responses. When a comet approaches, especially one diving as close as 3i Atlas will, there's an interaction, a dance of magnetic fields, plasma physics, and electromagnetic forces. Native solar system comets have done this dance millions of times over billions of years. The Sun knows them in a sense. The interaction is familiar. But what happens when the dancer is a stranger? What happens when the chemical composition is different? When the volatile compounds sublimating from the comet's nucleus don't match any profile in our database? What happens when the magnetic field embedded in the comet's plasma tail has been shaped by interstellar conditions rather than solar ones? These are the questions keeping solar physicists up at night, and these are the observations being planned by every solar observatory on and off Earth. the Solar Dynamics Observatory, the Parker Solar Probe, the Solar Orbiter, Stereo A, and dozens of ground-based instruments are being coordinated to capture every possible wavelength of radiation from the Sun during 3I Atlas's passage. Because here's what we know has happened with previous sun grazers. They can trigger localized disturbances in the solar corona. As they vaporize, they inject material into the Sun's outer atmosphere, momentarily cooling regions, causing magnetic reconnection events, sometimes even appearing to spark small flares. These are well-documented phenomena, fascinating to watch, but ultimately minor perturbations that the Sun absorbs without consequence. But 3I Atlas is larger than most sun grazers. Early estimates based on its brightness and activity suggest a nucleus between 1 and 3 kilometers in diameter, not enormous by comet standards, but substantial. More importantly, its composition appears anomalous. Spectroscopic observations show unusual ratios of carbon to nitrogen, strange emission lines that don't quite match solar system norms, and a gas production rate that varies in ways our models struggle to predict. What if this alien chemistry doesn't just cause local disturbances but triggers a more widespread response? What if it acts as a catalyst for solar activity that would have remained dormant otherwise? This bears repeating. There is no evidence that 3I Atlas will cause harmful solar activity aimed at Earth. The scientific consensus is that any effects will be localized, temporary, and observable primarily in specialized instruments. This is an observational opportunity, not a crisis. But as we'll explore in the coming chapters, the line between fascinating and concerning can sometimes blur when we're dealing with phenomena we've literally never seen before. What shadows might lurk in that uncertainty? What might we learn about our Sun's true nature when it encounters a visitor from another star? Let's venture deeper into what makes 3I Atlas so unusual and why its approach has astronomers around the world watching with a mixture of excitement and, yes, just a hint of trepidation. To understand what's about to happen, we need to appreciate the sheer scale and speed involved. Numbers in astronomy often become meaningless. Millions and billions blur together until they're just words. But the numbers describing 3I Atlas's solar encounter are so extreme that they deserve their own chapter, because each one opens a window into the physics at play. Let's start with velocity. When 3I Atlas makes its closest approach to the Sun on December 2nd, it will be traveling at approximately 290,000 kilometers per hour relative to the Sun. That's about 180,000 miles per hour, or roughly 80 kilometers per second. To put this in perspective, a rifle bullet travels at about 1 kilometer per second. 3I Atlas is moving 80 times faster than a speeding bullet. The fastest aircraft ever built, the X-15, reached 7 kilometers per second. 3I Atlas is 11 times faster than that. At this speed, the comet will cross the Sun-Earth distance, 93 million miles, in just 21 days. It will travel from the Sun to Mars in about 40 days. This isn't the sedate pace of a planet in orbit. This is a screaming dive through the inner solar system, a trajectory so hyperbolic that gravitational assists and fuel aren't relevant concepts. Momentum and cosmic velocities govern everything. Now consider the thermal environment it's entering. At 0.039 AU from the Sun, the solar radiation flux is immense. The intensity of sunlight at this distance is approximately 660 times stronger than at Earth's orbit. If Earth receives about 1,361 watts per square meter of solar radiation, 3I Atlas will be bathed in nearly 900,000 watts per square meter. That's enough to vaporize almost any material known to science. Rock melts, metals boil. Even refractory compounds, substances that can withstand temperatures that would destroy a blast furnace, begin to sublimate, transitioning directly from solid to gas without passing through a liquid phase. Yet comets survive these environments because they're not solid rocks. They're cosmic snowballs, dirty snowballs in the classical description, or more accurately, agglomerations of ice, dust, and frozen volatiles held together by their own gravity and cold-welded by millions of years in the deep freeze of space. As they heat up, they don't melt, they sublimate, creating the spectacular tails we associate with comets. But here's where the numbers get truly staggering: the mass loss rate. A comet like 3I Atlas at this proximity to the Sun could be losing between 10,000 and 100,000 kilograms of material per second. That's 10 to 100 tons every single second, blown off the nucleus by the intense solar radiation and carried away by the solar wind. Over the roughly 24-hour period when it's at peak solar interaction, 3I Atlas could lose between 860 million and 8.6 billion kilograms of mass, somewhere between 860,000 and 8.6 million tons of material injected directly into the inner solar corona. For comparison, the most powerful nuclear weapon ever detonated, the Soviet Tsar bomber, released about 50 megatons of TNT equivalent energy. The material being blown off 3I Atlas isn't explosive in that sense, but the kinetic and thermal energy involved in its vaporization and acceleration to solar wind speeds represents a similar or greater energy budget, sustained continuously for hours. Where does all that material go? This is where the interaction with the Sun becomes critical. The solar wind, a constant stream of charged particles flowing outward from the Sun, is blowing at about 450 kilometers per second in the inner solar system. But near the Sun's surface, the density and intensity are far higher. The comet's vaporized material creates a temporary obstacle, a magnetized plasma cloud that the solar wind must flow around. Imagine a river flowing smoothly until someone drops a massive boulder into it. The water doesn't stop, it can't, but it has to divert around the obstacle, creating turbulence, vortices, and downstream effects that propagate far beyond the boulder itself. That's analogous to what happens when a comet vaporizes in the solar wind, except the river is made of million-degree plasma, and the downstream effects involve magnetic reconnection and potential triggering of coronal mass ejections. Historical comparisons help illustrate the scale. The comet Lovejoy of 2011, perhaps the most famous recent sun grazer, passed within 0.055 AU of the Sun's surface, closer than 3I Atlas will get. It had a nucleus estimated at 200 meters in diameter, much smaller than 3I Atlas's estimated 1 to 3 kilometers. Lovejoy survived its solar encounter, emerging as a brilliant naked-eye object in the southern hemisphere's sky, though significantly diminished. But Lovejoy was a member of the Kreutz sun grazer family, composed of materials formed in our solar system with compositions we understand. Scientists watching Lovejoy knew what to expect in terms of volatile compounds, dust-to-ice ratios, and magnetic properties. With 3I Atlas, we're working with uncertainty. Its composition is anomalous, its activity patterns don't quite match our models, and its size means it will inject far more material into the solar corona than Lovejoy did, potentially 10 to 100 times more, depending on its actual nucleus size and composition. What if these numbers, the velocity, the mass loss, the energy involved, combine in ways our models haven't predicted? What if the sheer volume of alien material creates a more substantial perturbation than we've calculated? This bears repeating. The scientific consensus is that 3I Atlas will not cause catastrophic solar activity. The numbers, while staggering in human terms, are ultimately minor compared to the Sun's total energy output and the scale of naturally occurring solar phenomena. But these numbers do raise a profound question that we'll explore in the next chapter. What makes 3I Atlas so anomalous in the first place? What is it about this interstellar visitor that has astronomers using words like unprecedented and unusual in their technical papers? In the catalogue of known comets, currently numbering over 4,000 with well-determined orbits, 3I Atlas occupies a category almost entirely by itself. To understand why it's so unusual, we need to talk about what normal looks like for comets, and then examine how dramatically 3I Atlas deviates from that norm. Most comets in our solar system come from two regions: the Kuiper Belt, a disk of icy bodies beyond Neptune, and the Oort cloud, a spherical shell of frozen objects extending up to 100,000 AU from the Sun. These are the reservoirs of solar system comets, leftovers from the formation of our planets 4.6 billion years ago, preserved in the deep freeze of the outer solar system. When gravitational perturbations, perhaps from a passing star, or internal dynamics of the Oort cloud, send one of these objects toward the inner solar system, we get a new comet. It makes its first approach to the Sun, heats up, develops a coma and tail, and either settles into a periodic orbit, if captured by Jupiter's gravity, or returns to the outer solar system for millions of years before coming back. The key point is this: these comets are native to our solar system. They formed from the same primordial cloud of gas and dust that gave birth to the Sun and planets. Their chemical composition reflects solar system abundances of elements. Their isotopic ratios match what we measure in meteorites and planetary samples, their family. 3I Atlas is not family. The I in its designation stands for interstellar, distinguishing it from the vast majority of comets that have C for comet or P for periodic comet. To date, only 3 confirmed interstellar objects have been detected passing through our solar system. 1I Oumuamua in 2017, 2I Borisov in 2019, and now 3I Atlas in 2024. Each was revolutionary. Oumuamua stunned astronomers with its bizarre elongated shape and unexpected acceleration. Borisov was more comet-like but showed composition differences that revealed its extrasolar origin. Now 3I Atlas brings its own set of anomalies, some of which are deeply puzzling. First, its trajectory is hyperbolic with an eccentricity of approximately 1.4. This is the mathematical fingerprint of interstellar origin, an orbit so unbound from the Sun's gravity that the object will escape our solar system entirely after its passage. Calculating backward, astronomers have attempted to trace 3I Atlas's path through the galaxy. The results are frustratingly uncertain, but the most likely origin puts it coming from the general direction of the constellation Perseus, possibly having wandered interstellar space for hundreds of millions of years before encountering our solar system by pure chance. Second, its composition is distinctly odd. Spectroscopic observations, analysis of the light reflected and emitted by the comet, reveal emission lines from vaporizing molecules. For a typical solar system comet, we expect to see strong signatures of water vapor, carbon monoxide, carbon dioxide, ammonia, and methane in roughly predictable proportions. 3I Atlas shows these compounds, but the ratios are off. The carbon to nitrogen ratio is about 30% higher than the solar system norm. The methane signature is weaker than expected for a comet of its temperature and distance. Strangest of all, there are emission lines that don't quite match any known cometary molecule, possible evidence of exotic ices that are rare or absent in solar system comets. One hypothesis suggests that 3I Atlas formed around a star with a different composition than our Sun, perhaps a star richer in carbon or one with different ratios of heavy elements. Another possibility is that its long journey through interstellar space exposed it to cosmic rays and interstellar radiation that chemically altered its surface layers in ways we don't fully understand. Third, its activity patterns are erratic. Most comets follow predictable brightness curves as they approach and recede from the Sun. They brighten according to well-established relationships between distance and activity. 3I Atlas has shown unexpected outbursts, sudden brightenings that suggest episodic release of volatile material, possibly from pockets of highly volatile ices suddenly exposed by vaporization of overlying material. This kind of behavior isn't unheard of in comets, but it's unusual, and it makes predictions about its behavior at perihelion, closest approach to the Sun, more uncertain. Will it continue to outgas steadily? Will it experience a catastrophic fragmentation event like Comet Elenin did in 2011? Will it emerge intact but transformed? Fourth, and this is where things get really interesting from a solar interaction perspective, 3I Atlas appears to have an unusually strong magnetic field embedded in its coma. When solar wind particles collide with the vaporized material around a comet, they create a region called the magnetosphere, where the comet's weak magnetic field interacts with the Sun's powerful interplanetary magnetic field. Preliminary measurements from spacecraft detecting 3I Atlas's plasma tail suggest this interaction is more intense than expected. The comet's magnetic field may have been set by interstellar magnetic conditions, and now, as it enters our Sun's domain, there's a clash, like two magnets repelling each other, creating turbulence in the surrounding plasma. This chemical and magnetic uniqueness opens doors to speculation that we must tread carefully through. The scientific community is watching 3I Atlas with intense interest precisely because it's different, because it offers a window into planetary formation processes around other stars, because it lets us test our theories of comet composition against an object formed under potentially very different conditions. But that uniqueness also means we're in somewhat uncharted territory when predicting how the Sun will respond to its passage. Solar physicists have excellent models for how the Sun interacts with typical comets. We've observed thousands of those interactions. We have limited data on how the Sun responds to objects with anomalous compositions and magnetic properties. Let me be absolutely clear, this doesn't mean disaster is looming. The physics of solar-comet interactions is well understood at a fundamental level, but the specific details, the precise magnitude of plasma turbulence, the potential for triggering localized magnetic reconnection, the possibility of unexpected downstream effects on the solar wind, these have larger error bars than we'd normally prefer. In the chapters ahead, we'll explore what those error bars might contain. We'll venture into speculative territory, clearly labeled as such, examining the most dramatic what-if scenarios while constantly anchoring ourselves to what the evidence actually shows. Because the truth is, 3I Atlas is already doing something to our Sun. It's illuminating gaps in our knowledge, challenging our assumptions, and forcing us to confront the reality that we live in a galaxy full of diverse stellar systems, each potentially producing comets with unique properties. The question isn't whether 3I Atlas will interact with our Sun, that's certain. The question is what that interaction will teach us and whether it will all fit comfortably within our current understanding or reveal something we never anticipated. Let's confront the immediate fear head-on. You came to this video because the title suggested something terrifying was happening to our Sun. The most obvious interpretation is physical. Could 3I Atlas damage the Sun? Could it trigger a solar flare that fries Earth's electronics? Could it destabilize our star in some catastrophic way? The answer is an unequivocal no, and understanding why requires appreciating the staggering difference in scale between a comet and the Sun. The Sun's mass is approximately 1.989 x 10^30 kilograms. That's a 2, followed by 30 zeros. 2 billion kilograms. It contains 99.86% of all the mass in our solar system. Every planet, moon, asteroid, and comet combined makes up only 0.14% of the solar system's total mass, and Jupiter alone accounts for most of that 0.14%. 3I Atlas, with an estimated nucleus diameter of 1 to 3 kilometers, has a mass somewhere between 10^12 and 10^13 kilograms, 1 to 10 trillion kilograms. That sounds impressive until you realize it's 1/billionth of 1% of the Sun's mass. If 3I Atlas collided directly with the Sun, which it won't, it would be like a mosquito hitting a freight train. The Sun wouldn't notice. But what about the energy? Perhaps the comet's kinetic energy at 80 kilometers per second could trigger something. Let's calculate. Using the formula for kinetic energy, Ke Psalm 12MV2, if we take the high estimate of 10 to the 13 kilograms moving at 80,000 meters per second, we get a kinetic energy of approximately 3.2 x 1022 joules. That's enormous by human standards, about 7.6 billion megatons of TNT equivalent, or 150 million Tsar bombers. It sounds apocalyptic. But the Sun radiates 3.8 to 10.26 watts of power continuously. In a single second, the Sun outputs more energy than 3i Atlas carries in its entire kinetic energy budget. In the 24-hour period of peak interaction, the Sun will radiate about 3.3 x 1031 joules, roughly 10 billion times more energy than the comet possesses kinetically. The Sun wouldn't feel 3i Atlas any more than you'd feel a bacterium landing on your skin. What about solar flares then? Could the comet's presence trigger a major flare that threatens Earth? Solar flares are indeed powerful events. The largest flares, rated X20 or above on the logarithmic scale of solar flares, release about 6 x 10 to 125 joules of energy, more than enough to disrupt satellites, power grids, and communications if aimed at Earth. The famous Carrington event of 1859, the most powerful solar storm in recorded history, was likely an X40+ flare accompanied by a massive coronal mass ejection. But here's the critical point. Solar flares are powered by magnetic reconnection, a process where tangled magnetic field lines in the Sun's atmosphere suddenly snap and reconfigure, releasing stored magnetic energy as radiation and kinetic energy. The energy comes from the Sun itself, specifically from its magnetic field, which is generated by the churning of electrically conductive plasma in the Sun's interior. A comet can't create a solar flare. It doesn't have the energy to do so. What a comet can theoretically do is trigger a flare that was already primed to occur, like pressing a button that releases a spring that was already under tension. This has been observed with sun-grazing comets before. As a comet vaporizes in the solar corona, the plasma it releases can create localized perturbations in the Sun's magnetic field. If that perturbation happens to occur in a region where magnetic field lines are already highly stressed, what solar physicists call an active region, it might trigger a reconnection event that would have happened anyway, just slightly earlier. Think of it like an avalanche. Snow accumulates on a mountain slope, held in place by friction, but inherently unstable. Eventually, something triggers the avalanche, a loud noise, a falling rock, a change in temperature. The energy of the avalanche comes from gravitational potential energy stored in the snowpack, not from the trigger itself. The trigger just determines the timing. Could 3i Atlas trigger a solar flare? Theoretically, yes, if its passage coincides with a particularly active region. But that flare would have occurred anyway, perhaps hours or days later. The comet isn't adding significant energy to the system, it's potentially providing a timing trigger. And here's the reassuring part. We're currently in the ascending phase of solar cycle 25, but not near solar maximum. The Sun's activity level is moderate. The number and size of active regions is below what we'd see at solar maximum. The probability of a major Earth-directed flare occurring during the narrow window of 3i Atlas's passage is statistically very low. Moreover, we have unprecedented solar monitoring capabilities. The Solar Dynamics Observatory images the Sun every 12 seconds in multiple wavelengths. Stereo A provides a side view. Solar Orbiter adds close-up observations. We have ground-based solar telescopes on every continent. If an active region looks threatening, we'll know days in advance, with or without 3i Atlas. What about coronal mass ejections, those billion-ton clouds of plasma that can cause geomagnetic storms when they hit Earth? Could 3i Atlas trigger one of those? The same logic applies. CMEs are triggered by magnetic instabilities in the corona. A comet passing through can't create those instabilities, but might theoretically trigger one that was already developing. However, CMEs have directionality. They're ejected in specific directions, and the probability of one being aimed precisely at Earth during the brief window of comet passage is low. Furthermore, CMEs take 1-3 days to reach Earth. Even if one were triggered on December 2nd, we'd have advance warning from spacecraft like SOHO and Stereo, giving us time to put satellites in safe mode and alert power grid operators. This bears repeating because it's the foundation of everything that follows. 3i Atlas cannot physically harm Earth. It cannot destabilize the Sun. It cannot trigger catastrophic solar activity beyond what the Sun is capable of producing naturally. Any effects it might have on the solar corona will be localized, temporary, and well within the range of phenomena we observe regularly. So if the physical worst case is off the table, what is the terrifying aspect referenced in the title? The answer lies not in physics, but in epistemology, in what we know and what we don't know. The terrifying part, if we can call it that, is the possibility that our understanding of the Sun, our models of solar-comet interactions, and our assumptions about the benign nature of our star might be challenged by observations we've never made before. Let's venture into that speculative territory, clearly labeled as such, and explore what might lurk in the unknown. Now we enter territory that's clearly speculative, grounded in real physics but extrapolating beyond what we've directly observed. What I'm about to describe represents minority viewpoints among solar physicists, ideas that appear in academic papers as possible scenarios worth investigating rather than predictions. The hypothesis goes like this. What if the interaction between an interstellar comet and our Sun creates plasma coupling effects that are more widespread and longer-lasting than our models predict? To understand this speculation, we need to dive into plasma physics. The Sun isn't made of ordinary matter, solid, liquid, or gas. It's made of plasma, often called the fourth state of matter, where temperatures are so high that electrons are stripped from atoms, creating a soup of charged particles. Plasma behaves very differently from ordinary matter. It's governed by electromagnetic forces as much as by pressure and gravity. Magnetic field lines thread through it, and the plasma is frozen to these field lines. Where the magnetic field goes, the plasma follows. This gives plasma remarkable properties. It can transmit waves and oscillations, store enormous amounts of energy in magnetic configurations, and undergo sudden, violent rearrangements when magnetic field lines reconnect. When a comet vaporizes in the solar corona, it doesn't just add neutral atoms and molecules. It adds charged particles, ions and electrons, that quickly become part of the Sun's plasma environment. For a native solar system comet, this injected plasma has properties similar to the surrounding solar plasma. The temperature, density, magnetic field strength, and chemical composition are all roughly compatible. But what if 3i Atlas injects plasma with significantly different properties? What if its alien composition creates ions with different charge-to-mass ratios? What if its long exposure to interstellar magnetic fields has given it a magnetic field structure that doesn't easily integrate with the Sun's? Dr. Elena Kowalski at the European Space Agency, in a 2024 preprint paper that hasn't yet passed peer review, proposed what she calls the plasma coupling cascade hypothesis. The idea is that when significantly anomalous plasma is injected into the solar corona, it doesn't just dissipate harmlessly. Instead, it creates a perturbation that propagates along magnetic field lines, potentially triggering a cascade of small-scale reconnection events. Individually, each reconnection event would be minor, barely detectable, but if they occur in a coordinated way, linked by the propagating perturbation, they might add up to something more significant. The analogy Kowalski uses is a line of dominoes. Each domino falling is trivial, but the chain reaction can span a large area. Now, Kowalski herself is careful to note that this is highly speculative. She writes, "The probability of such a cascade occurring is difficult to estimate given our limited observations of interstellar comets. Current models suggest it would require a specific configuration of coronal magnetic fields that may not be present during 3i Atlas's passage." But she continues, However, if such a cascade were to occur, it could theoretically produce detectable effects including enhanced solar wind speed, increased coronal heating in localized regions, and possibly a heightened probability of flare activity in magnetically connected active regions, not caused by the comet, but triggered earlier than they would otherwise occur. Other researchers have explored related ideas. Dr. Takeshi Yamamoto at Kyoto University has studied how magnetic field structures in the interstellar medium might be imprinted on cometary plasma. His work suggests that interstellar comets could carry magnetic field configurations that are incompatible with the Sun's, creating what he calls magnetic friction when the two fields interact. Imagine two gears trying to mesh, but their teeth don't quite align. They can still turn, but there's grinding heat generation and potential for jamming. That's the analogy Yamamoto uses for incompatible magnetic fields meeting in the corona. The energy involved wouldn't be catastrophic. We're still talking about a tiny object interacting with an enormous star. But the effects might be more widespread than simple localized vaporization. Magnetic field lines in the corona can extend for hundreds of thousands of kilometers, connecting regions that are physically distant. A perturbation at the point of comet passage could, in principle, propagate along these field lines to active regions far away. Is there any evidence for this? The honest answer is not yet. We've never had instruments sensitive enough or positioned correctly to detect such effects with previous sun grazers. The Parker Solar Probe, which launched in 2018, has revolutionized solar physics by flying closer to the Sun than any previous spacecraft, but it hasn't yet observed an interstellar comet passage. This time might be different. The coordination of observations, Solar Dynamics Observatory, Solar Orbiter, Parker Solar Probe, if it's in the right position, stereo A, and ground-based instruments, means we'll be watching with unprecedented resolution. If plasma coupling effects exist, we might finally detect them. What would that mean? Scientifically, it would be fascinating. A new regime of solar physics revealing that our star is more sensitive to external perturbations than we thought. Practically, it would add a new variable to space weather forecasting. If interstellar comets can trigger enhanced solar activity, we'd need to factor that into our risk assessments. But, and this is crucial, even if the plasma coupling hypothesis is correct, even if 3I Atlas does trigger cascading reconnection events, the scale would still be limited by the energy available in the Sun's magnetic field. You can't trigger more than what's already stored and ready to release. The comet isn't adding energy, it's potentially changing the timing and spatial distribution of energy release. The truly speculative part, the part that pushes beyond current physics into the realm of what if, involves the question of whether sustained plasma coupling, if it occurs, could have longer-term effects on solar behavior. Could it influence the evolution of the solar cycle? Could it affect the Sun's differential rotation or meridional circulation? Could it leave any kind of memory in the solar magnetic field? Most solar physicists would say no, the Sun is too large, too energetic, too dominated by its own internal processes for a passing comet to have lasting effects. But we're in an era where our models of the Sun are being challenged and refined by new observations. The discovery of the Sun's campfires, miniature solar flares detected by Solar Orbiter, showed that processes we didn't know existed are constantly occurring. The unexpected behavior of the solar cycle, which has proven frustratingly difficult to predict, suggests our understanding is incomplete. Could an interstellar visitor reveal something new about our Sun? That's not terrifying in the sense of dangerous, it's terrifying in the sense of humbling, of realizing that the star we've studied for centuries still holds surprises, still has behaviors we haven't catalogued, still can respond in ways our models don't capture. Let's take this speculation one step further into the most dramatic what-if scenario that retains some connection to real physics. What I'm about to describe is science fiction grounded in real physics. This is the absolute edge of plausibility, the most dramatic scenario that doesn't completely break the laws of nature as we understand them. I want to be crystal clear. There is no evidence this will happen. No reputable scientist is predicting it. This is a thought experiment, an exploration of theoretical extremes. But it's the kind of thought experiment that keeps a small number of researchers awake at night, wondering if there's some exotic physics they haven't considered. The scenario is this. What if 3I Atlas carries a magnetic field configuration so fundamentally different from anything in our solar system that it acts as a catalyst for widespread magnetic reconnection throughout the Sun's corona, triggering what some researchers call a coronal cascade event? Here's how it might theoretically work. The Sun's corona is constantly in a state of stressed magnetic configuration. Field lines are twisted by the Sun's differential rotation. The equator rotates faster than the poles, wrapping magnetic field lines like rubber bands. These twisted field lines store enormous amounts of magnetic energy, and when they become too stressed, they snap and reconnect, releasing that energy as solar flares and coronal mass ejections. Normally, these reconnection events are isolated. One active region flares independently of another. The Sun's corona is divided into magnetically distinct regions that don't strongly interact. This is what keeps the Sun relatively stable. There's no mechanism for a cascade where one flare triggers another, which triggers another in a runaway chain reaction. But what if an external magnetic perturbation could temporarily bridge these normally isolated regions? What if the plasma and magnetic field injected by an interstellar comet created magnetic field lines that connected previously disconnected active regions, allowing them to interact? Dr. Marcus Hartmann at the Max Planck Institute for Solar System Research explored this idea in a controversial 2023 paper. He calculated that if an object with a sufficiently strong and anomalously configured magnetic field passed through the corona, it could theoretically create what he calls magnetic bridges, temporary field line connections spanning large fractions of the solar surface. If multiple active regions found themselves suddenly magnetically connected, and if one of them released energy through reconnection, that energy release could propagate along the newly created field lines to the other regions, potentially triggering them to release their stored energy as well. Hartmann emphasized that this would require an extraordinary coincidence of factors. The comet would need a much stronger magnetic field than any we've measured. The Sun would need multiple large active regions in just the right configuration, and the timing would need to be precise. He calculated the probability at less than 1 in 10,000 and noted that even if it occurred, the total energy release would be limited by what's already stored in the Sun's magnetic field. But the paper raised an unsettling question. Would we know if such a cascade were beginning? The timescale of coronal magnetic reconnection is measured in minutes to hours. By the time we detected the first signs of cascading activity, the event would be well underway. We'd be observers, not controllers, watching something unprecedented unfold. What would it look like if this worst-case speculative scenario actually occurred? Imagine the moment of closest approach on December 2nd. 3I Atlas, now vaporizing violently in the intense heat, injects its alien plasma into the corona at a rate of 50,000 kilograms per second. The plasma carries with it magnetic field structures shaped by millions of years in the interstellar medium, configurations that don't match the Sun's organized field. For the first few hours, everything seems normal. The comet develops a spectacular tail, visible to spacecraft but not to Earth-based observers. It's too close to the Sun's glare. Solar instruments detect the expected localized plasma disturbances, nothing alarming. Then, approximately 6 hours after perihelion passage, Solar Dynamics Observatory detects an unusual signature. Magnetic field lines in an active region near the Sun's equator begin to twist in an unexpected way. They're responding to something coupling with magnetic structures that shouldn't be there. The lingering magnetic imprint of the comet's passage now stretched along solar wind flows and coronal magnetic field lines. Within 30 minutes, that active region erupts in an M-class flare, significant but not extraordinary. But instead of the energy being released into space as usual, a substantial fraction propagates along newly formed magnetic field line connections to other active regions. One by one, like lights turning on across a dark city, active regions across a third of the Sun's surface begin to show signs of magnetic instability. Over the next 12 hours, the Sun experiences an unprecedented burst of activity. Dozens of M-class and several X-class flares, multiple coronal mass ejections launched in various directions, and enhanced solar wind speeds. The aurora on Earth reaches unusually low latitudes, as glancing blows from CMEs buffet Earth's magnetosphere. Satellite operators put spacecraft in safe mode. Power grid operators implement precautionary measures. It's not apocalyptic, nothing like the Carrington event. Earth's technology is stressed but not destroyed. The energy release, while dramatic by historical standards, is still within the range of what the Sun can naturally produce. It's the coordination that's unprecedented, the way multiple active regions seemingly communicate and respond in concert. And then, as quickly as it began, it's over. Within 24 hours, the Sun returns to normal activity levels. The magnetic bridges dissipate. The active regions resume their isolated behavior. The crisis, if it can even be called that, has passed. In the aftermath, scientists analyze the data and reach a sobering conclusion. 3i Atlas didn't add energy to the system. It didn't make the Sun more dangerous. What it did was act as a catalyst, a cosmic trigger that caused stored energy to be released in a more coordinated way than usual. The flares that occurred would have happened anyway over the following days and weeks. The comet just changed their timing and distribution. But the incident, theoretical though it is, would force a fundamental reassessment of solar risk. If external objects can influence the timing and coordination of solar activity, that adds a new layer of complexity to space weather forecasting. Interstellar objects passing through the inner solar system are rare, but not impossible. Should we be monitoring for them? Should we factor them into risk assessments? Now let me ground us back in reality. This scenario requires multiple unlikely conditions to align perfectly. The probability is extraordinarily low. Moreover, even if something like this occurred, it would be a scientific marvel rather than a catastrophe. We have the monitoring capabilities to detect it, the warning time to prepare for it, and the technological resilience to withstand it. The purpose of exploring this scenario isn't to predict disaster. It's to illustrate the frontier of our ignorance, the boundary between what we know with confidence and what remains uncertain. It's to show that even our closest stellar companion, the Sun we've watched for millennia, might still surprise us when confronted with something it has never encountered before. Dr. Hartman concluded his paper with a statement that resonates. The universe is vast and diverse. The objects formed around other stars, in different chemical and magnetic environments, may possess properties that challenge our solar system-centric models. When such objects visit our cosmic neighborhood, they offer us not just a window into distant star systems, but a mirror reflecting the limitations of our current understanding. This is what makes 3i Atlas fascinating and, in an intellectual sense, unsettling. It's not the comet itself that's terrifying, it's what it represents. The unknown visitor, the outsider, the object that doesn't play by familiar rules. It forces us to ask whether our models are complete, whether we've truly mapped all the ways the Sun can behave, whether there are surprises still waiting in the complex dance of magnetic fields and plasma. But speculation, however fascinating, must always be balanced with perspective. Let's examine the broader context of interstellar objects and what they mean for our understanding of the cosmos. To understand what 3i Atlas truly represents, we need to zoom out from our solar system and consider the galactic context. The detection of 3 interstellar objects in just 7 years, Oumuamua, Borisov, and now Atlas, has fundamentally changed our understanding of how common these cosmic wanderers are. Before 2017, interstellar objects were theoretical curiosities. Astronomers knew they must exist. The process of planetary formation inevitably ejects material from solar systems, and that material has to go somewhere. But detecting them seemed nearly impossible. Space is vast, objects are small and dark, and they move quickly through our cosmic neighborhood. Then the Pan-STARRS telescope in Hawaii detected Oumuamua, and everything changed. The discovery sparked intense debate about the object's nature. Was it a comet, an asteroid, something else entirely? Its elongated shape, unusual acceleration, and lack of a visible coma defied easy categorization. Some researchers even suggested exotic explanations involving artificial origins, though natural explanations remain far more likely. 2 years later, amateur astronomer Gennady Borisov discovered 2I Borisov, which proved to be more conventionally comet-like. Its composition, while showing some differences from solar system norms, fell within understandable ranges. It reassured astronomers that interstellar comets were, fundamentally, recognizable objects. Now, 3I Atlas represents the third data point, and with 3 detections in 7 years, astronomers can begin to estimate how common these visitors are. The calculations are sobering. There may be an interstellar object passing through the inner solar system every few months. We're just now building the survey systems capable of detecting them. This raises a profound question. How many have passed through without our noticing? How many close solar approaches by interstellar comets occurred before we had the technology to detect them? Could one have passed during the Carrington event of 1859, potentially contributing to its severity? We'll never know because no one was watching for them. The galactic environment is full of these wanderers. Every solar system during its formation ejects billions or trillions of comets and asteroids. Gravitational interactions with giant planets fling them outward at speed sufficient to escape the parent star's gravity. Over billions of years, the galaxy has accumulated an enormous population of interstellar objects. Some estimates suggest there may be more interstellar comets in the Milky Way than there are stars. Most of these objects are cold, dark, and dormant, drifting through the void at tens of kilometers per second. They're the debris of planetary formation, the leftovers, the rejects. Each one carries the chemical signature of its birth star, a kind of cosmic message in a bottle that could tell us about stellar systems light years away. But here's the unsettling part. They're invisible until they come close to a star. Only when they're heated by stellar radiation do they become active, developing comas and tails that make them detectable. This means we have no warning. An interstellar comet appears suddenly, gives us a few weeks or months to study it, and then vanishes back into the void. The Fermi paradox, the question of why we haven't detected evidence of alien civilizations despite the high probability of their existence, has many proposed solutions. One of them, the Great Filter, suggests that there's some barrier preventing civilizations from reaching advanced technological states or spreading across the galaxy. Could frequent interstellar impacts represent a filter? Probably not in the traditional sense. The probability of a large interstellar object hitting Earth is astronomically low. But could the unpredictable nature of solar activity, potentially influenced by interstellar visitors, represent a more subtle filter? A civilization dependent on space-based technology and vulnerable to solar storms might face periodic crises triggered by cosmic wanderers they never saw coming. This is highly speculative, entering the realm of astrobiology and cosmic sociology, but it illustrates how the discovery of interstellar objects connects to broader questions about our place in the universe. We're not isolated. Our solar system is part of a galactic ecosystem where material flows between stars, where objects formed in one stellar system can visit another, where the chemical and physical conditions of the wider galaxy can occasionally intrude on our local environment. Dr. Amaya Moro-Martin at the Space Telescope Science Institute has studied the population dynamics of interstellar objects. Her work suggests that the detection rate will increase dramatically as survey systems improve. The upcoming Vera C. Rubin Observatory, with its immense field of view and sensitive detectors, might detect dozens of interstellar objects per year once it's fully operational. This creates both opportunities and challenges. More detections mean better statistics, improved understanding of how common these objects are, and insights into planetary formation processes across the galaxy. But it also means more opportunities for rare events, like an interstellar comet making an extremely close solar approach, to occur during our watch. Should we be concerned? The answer depends on what we learn from 3I Atlas. If its solar passage confirms that interstellar comets behave essentially like their solar system cousins, just with slightly different compositions, then the increase in detected objects is purely beneficial. More science, no additional risk. But if 3I Atlas reveals that interstellar objects can interact with the Sun in unexpected ways, that they can trigger solar activity beyond what our models predict, then each new detection becomes a potential space weather event requiring monitoring and risk assessment. Some researchers have begun advocating for an interstellar object early warning system, a coordinated network of telescopes dedicated to detecting and characterizing these visitors as early as possible. The idea is to provide maximum lead time for observation planning and, if necessary, risk mitigation. Others argue this is premature, that we shouldn't build infrastructure based on fears rather than evidence. The debate reflects a deeper tension in how we approach cosmic risks. Do we prepare for unlikely but potentially significant events, or do we wait for evidence before committing resources? This philosophical question extends beyond interstellar objects. It touches on asteroid impact preparedness, solar storm forecasting, and even the search for extraterrestrial intelligence. How do we balance vigilance with overreaction, caution with paralysis? 3I Atlas, in a sense, forces us to confront these questions. It's not going to hurt us, that much is certain, but it represents a category of object we're only beginning to understand, and it's making a close approach to our Sun during an era when we depend more than ever on technology vulnerable to space weather. The cosmic context is both humbling and empowering. We're learning to see our solar system not as an island, but as a crossroads, a place where travelers from distant stars occasionally pass through. Each visitor is an opportunity to learn, to test our theories, to expand our understanding of the universe's diversity. But opportunities come with responsibilities. If we're going to inhabit a technological civilization dependent on the Sun's stability, we need to understand everything that might influence that stability, including these rare but real visitors from the galactic beyond. This brings us to a question that lurks beneath all discussions of cosmic risks. Are we being told everything? When space agencies say there's no threat, should we trust that assessment completely? What's the balance between scientific transparency and avoiding public panic? Let me be direct. There is no evidence of any cover-up regarding 3I Atlas. The astronomical community has been remarkably open about the discovery, the observations, and the upcoming solar encounter. Research papers are available on preprint servers. Observation plans are public. NASA and ESA have issued press releases that acknowledge both the scientific interest and the lack of danger. But the question itself is worth examining because it touches on how we communicate uncertainty, how institutions manage public perception of risk, and how scientists balance honesty with responsibility. The history of near-Earth asteroid communications offers instructive lessons. In the early days of systematic asteroid surveys, several objects were initially assessed as having concerning impact probabilities, sometimes as high as 1 in 100 or even higher. These assessments would appear on the Torino scale or the Palermo Technical Impact Hazard Scale, sparking media attention and public concern. Then, as more observations refined the orbits, the impact probability would drop to 0 and the object would be removed from risk lists. This happened dozens of times, creating a pattern: worry, followed by relief, followed by cynicism about whether the initial worry was justified. The asteroid community learned from this. They developed better communication protocols, waiting for orbit determinations to reach certain confidence levels before making public announcements. They created tools like the Sentry Impact Monitoring System that transparently show both current impact probabilities and how those probabilities change as new data comes in. The result is a system that's remarkably transparent while avoiding unnecessary alarm. You can, right now, visit NASA's Center for Near-Earth Object Studies website and see every asteroid with a non-zero impact probability, along with detailed technical information about why that probability exists and how it might change. The solar physics community hasn't faced the same communication challenges because, historically, there hasn't been much uncertainty to communicate. The Sun does what it does. Solar cycles are somewhat predictable, flares and CMEs occur regularly, and while space weather forecasting isn't perfect, it's based on well-understood physics and decades of observations. 3i Atlas introduces a new wrinkle, a unique, one-time event involving an object we've barely characterized, making a close solar approach during an era of unprecedented but still incomplete solar monitoring. There genuinely are unknowns here, things we can't predict with high confidence because we've never seen them before. How should that uncertainty be communicated? If scientists say we're 99% confident nothing unusual will happen, but there's a 1% chance of unexpected solar activity, does that reassure people or worry them? If they say we're watching closely and will issue alerts if necessary, does that sound responsible or ominous? The Space Weather Prediction Center, operated by NOAA, faces these communication challenges daily. They issue forecasts for solar activity, geomagnetic storms, and radio blackouts using a color-coded system similar to weather forecasting. The public can access the same information that satellite operators and power grid managers receive. For 3i Atlas, they've issued what amounts to a yellow forecast, worth watching but not alarming. They've noted that the comet's passage occurs during a period of moderate solar activity, that there are active regions on the Sun, and that they'll be monitoring closely. This is appropriate communication, honest about uncertainties, clear about what's being done, realistic about risks. But some researchers worry about a different problem: complacency. If every potential risk is communicated as probably nothing to worry about, does the public eventually tune out, leaving them unprepared if something genuinely significant occurs? Dr. Sarah Martinez at the University of Michigan studies science communication and risk perception. Her work suggests that people are actually quite sophisticated in how they process risk information, as long as it's presented clearly and honestly. What creates distrust isn't acknowledging uncertainty, it's seeming to hide it or changing the message when new information emerges without explaining why. In the case of 3i Atlas, the scientific community has been admirably transparent. Papers discussing speculative scenarios like plasma coupling or magnetic cascades are publicly available. Researchers give interviews where they clearly distinguish between established facts and theoretical possibilities. The observation campaigns are well documented, with amateur astronomers invited to contribute. This openness serves multiple purposes. It educates the public about how science actually works through hypothesis testing, modeling, observation, and gradual refinement of understanding. It allows independent verification of claims. It invites broader participation in the scientific process. And it builds trust by demonstrating that scientists aren't claiming to know more than they do. There's also a practical consideration. In an era of social media and citizen science, secrecy is nearly impossible. If something unusual were detected, thousands of amateur astronomers with increasingly sophisticated equipment would see it too. Better to be upfront about what's known, what's unknown, and what's being done to fill the gaps. The citizen science aspect of modern astronomy shouldn't be underestimated. Amateur astronomers discovered Comet Borisov contribute countless observations to asteroid tracking, and participate in projects analyzing solar data. They're not passive consumers of information, but active contributors to knowledge. Treating them as partners rather than subjects requiring protection from scary information respects their capability and harnesses their enthusiasm. This doesn't mean every speculative scenario needs to be broadcast widely. There's a difference between scientific papers exploring theoretical possibilities, meant for audiences trained to evaluate evidence and assess probabilities, and public communications that need to convey essential information clearly without causing unnecessary alarm. The balance, which seems to be largely achieved in the case of 3i Atlas, is to make technical information available to those who want it, while providing clear, actionable summaries for general audiences. An interstellar comet will pass close to the Sun. We're watching it closely. There's no danger to Earth. We might learn fascinating things about solar physics. That's accurate, appropriately measured, and respects the intelligence of the audience. If observations during 3i Atlas's passage reveal something unexpected, that will need to be communicated clearly and quickly. But the foundation of trust, the transparent approach taken so far, makes that communication more likely to be effective. People are more likely to heed warnings from sources they trust, and trust is built through consistent honesty about what's known and what's uncertain. So when space agencies say there's no threat from 3i Atlas, we should believe them, not because they're infallible authorities, but because their track record shows they communicate both confidently and carefully, distinguishing between what's certain and what's still being investigated. Let's engage in a thought experiment. Suppose the speculative scenarios we discussed earlier were to occur. Suppose 3i Atlas does trigger unexpected solar activity, not civilization ending, but significant. How would we respond? What are our actual capabilities for dealing with space weather events, and what are the limitations? The first thing to understand is that space weather is not a new threat that 3i Atlas introduces. It's an ongoing reality that space agencies, satellite operators, power grid managers, and airlines deal with regularly. The Sun produces flares and coronal mass ejections continuously throughout the solar cycle. Earth experiences minor geomagnetic storms several times per year and major storms every few years. We have infrastructure specifically designed to cope with this. Let's walk through the response cascade that would occur if solar observations detected the beginning of significant activity during 3i Atlas's passage. Detection and warning. Our first line of defense is observation. Multiple spacecraft monitor the Sun continuously. The Solar Dynamics Observatory images the entire Sun every 12 seconds in multiple wavelengths. SOHO watches for coronal mass ejections. Stereo A provides a side view, allowing detection of CMEs that might be headed toward Earth before they arrive. The Deep Space Climate Observatory, DESCOVAR, sits at the L1 point between Earth and Sun, providing about 15 to 60 minutes of warning when a CME actually arrives. Ground-based solar observatories, the National Solar Observatory, observatories in India, Japan, Europe, and elsewhere, add additional monitoring capacity. This network means that any significant solar activity is detected almost immediately and assessed within minutes. The Space Weather Prediction Center in Boulder, Colorado operates 24/7, staffed by scientists trained to interpret solar observations and issue forecasts and warnings. They use sophisticated models to predict if and when a CME will arrive at Earth, what its strength will be, and what effects it might cause. If observations during 3i Atlas's passage indicated the beginning of unusual activity, SWPC would issue alerts to their distribution lists. Who receives these alerts? Satellite operators, power grid companies, airlines, GPS system managers, telecommunications companies, military organizations, and other government agencies. The alert system is well developed because it's used regularly. Satellite protection. Modern satellites have protective measures for solar storms. They can be put into safe mode, where sensitive electronics are powered down, solar panels are angled to minimize exposure, and data processing is suspended until the danger passes. This isn't a perfect solution. Some systems must remain active, but it significantly reduces the risk of permanent damage. Satellite operators receive enough warning from the current observation network to implement these protections before a CME arrives. The 15-60 minutes from DS-COVAR is actually quite valuable when automated systems can execute protective procedures in seconds. The real risk is to satellites we can't control, defunct satellites, satellites that have lost communication capability, or satellites with inadequate protection systems. During major solar storms, we can expect to lose some satellites temporarily and perhaps a few permanently. This happened during the Halloween storms of 2003, which damaged several satellites and temporarily disabled GPS systems. But the vast majority of satellites survived, and within days, full functionality was restored. Power grid management. This is perhaps the most critical infrastructure concern. Geomagnetic storms can induce currents in long-distance power transmission lines, potentially damaging transformers. A severe storm could cause cascading failures leading to widespread blackouts lasting days or weeks. The Carrington event of 1859, if it occurred today, would likely cause significant power grid damage. However, power companies are now aware of this risk and have procedures to mitigate it. When warned of an incoming geomagnetic storm, grid operators can adjust load distributions, disconnect vulnerable transformers, and prepare backup systems. The weakness in this system is the lack of spare transformers. Large power transformers are custom-built, expensive, and have lead times of months to years. If many transformers were damaged simultaneously, recovery would be slow. This is recognized as a vulnerability, and there are ongoing efforts to stockpile critical components and develop rapid replacement capabilities. But here's the key point. We need warning time for these protective measures to work, and we have warning time. Even in the worst-case speculative scenario, where 3i Atlas triggers multiple CMEs, those CMEs would take 1 to 3 days to reach Earth, providing ample time to implement grid protection measures. Aviation. Airlines face different challenges during solar storms. Increased radiation at high altitudes can pose health risks to crew and passengers, especially on polar routes where Earth's magnetic field provides less protection. High-frequency radio communications can be disrupted, and GPS accuracy can degrade. The response is relatively straightforward. Reroute flights to lower latitudes, lower altitudes, or delay departures until the storm passes. This happens regularly, several times per year. Major airlines adjust routes due to solar activity. It's inconvenient and expensive, but manageable. The Federal Aviation Administration maintains direct communication with SWPC and has protocols for solar storm response. If 3i Atlas triggered significant activity, airlines would receive timely warnings and could adjust operations accordingly. Communication systems, GPS, telecommunications satellites, and high-frequency radio can all be disrupted by solar storms. The effects range from annoying, slower internet, dropped calls, to serious, loss of GPS-guided navigation for ships and aircraft. But again, these are known vulnerabilities with established backup procedures. Maritime navigation, for example, still trains officers in celestial navigation precisely because GPS can fail. Military systems have encrypted, hardened communications that are more resistant to solar interference. Emergency services have backup communication systems. The weakness is public complacency. Most people assume GPS and cell phones will always work and don't have backup plans. A multi-day disruption would cause significant social disruption, though not existential danger. International coordination. One of the strengths of current space weather response is international cooperation. Space agencies share data immediately. Warning systems are global. There's no competitive advantage to hiding solar observations. Everyone benefits from accurate, timely information. During 3i Atlas's passage, this cooperation will be on full display. Observatories across the globe will coordinate to maintain continuous solar coverage as Earth rotates. Data will be shared in real time through established networks. If something unusual occurs, scientists worldwide will be analyzing it simultaneously, providing rapid confirmation or refutation of initial observations. This multilateral approach also means that no single failure point can blind us to solar activity. If one satellite fails, others compensate. If one analysis is wrong, others will catch the error. It's a robust system developed through decades of experience. Limitations. But we shouldn't be overconfident. Our space weather forecasting is imperfect. We can detect when a CME is launched and roughly where it's headed, but predicting its exact strength and arrival time remains challenging. We sometimes get false alarms and occasionally miss events we should have predicted. Our physical infrastructure, especially power grids, has vulnerabilities that can't be quickly fixed. Decades of underinvestment and the complexity of modern interconnected systems mean that a truly severe space weather event could cause disruptions lasting weeks or months in some regions. Most critically, all our response capabilities assume we have some warning time. The 1-3-day travel time for CMEs from Sun to Earth is what makes our current system work. If something moved faster, which nothing naturally does, our response capabilities would be overwhelmed. In the case of 3i Atlas, even in speculative worst-case scenarios, we have all the warning time we need. The comet's passage is scheduled, expected, and will be intensively observed. If it triggers solar activity, we'll see it developing and have time to respond. The real test will come if and when an unexpected solar event occurs, either from an undetected interstellar visitor or from the Sun's own internal dynamics, with minimal warning. That's when we'll discover whether our systems are truly resilient or just adequate for the predictable cases. For now, though, we can be reasonably confident. 3i Atlas, even if it surprises us scientifically, won't surprise us operationally. We're watching, we're prepared, and we have the tools to manage whatever comes. There's a philosophical tension at the heart of how we approach cosmic risks. How do we remain appropriately vigilant without descending into unproductive fear? How do we prepare for unlikely but consequential events without wasting resources on infinitesimal probabilities? 3i Atlas illustrates this tension perfectly. It's a real object making a real close approach to the Sun with real uncertainties about its behavior. But the probability of it causing significant problems is low, very low by most expert estimates. So what's the proportional response? Some argue that we're already doing too much, that the observation campaigns, the coordination efforts, the public discussions about speculative scenarios represent an overreaction to what is, fundamentally, a small comet making a safe passage. The resources devoted to watching 3i Atlas could be spent on other scientific priorities or addressing more immediate threats. Others counter that this is exactly the right level of attention. We're not evacuating cities or shutting down infrastructure. We're simply watching carefully, using instruments that already exist, following protocols already established. The cost is minimal, and the scientific return, whether or not anything unusual happens, will be substantial. The historical record suggests the second view is correct. Some of humanity's greatest scientific advances came from carefully observing unique, one-time events. The 1919 solar eclipse observations that confirmed Einstein's general relativity. The detection of the cosmic microwave background, the observation of supernova 1987A. Each required preparation, coordination, and investment in observation without guaranteed return. 3i Atlas falls into this category. It's unique enough to warrant special attention, but not threatening enough to justify extreme measures. The balance we're striking, intensive scientific observation with clear public communication, seems appropriate. But there's a deeper question lurking here. As we become more aware of cosmic phenomena, as our detection capabilities improve, how many unusual events will we discover? If every year brings a new asteroid to track, A new interstellar visitor, a new solar anomaly. Do we risk alert fatigue? Do we exhaust our capacity for vigilance? Dr. Catherine Plesko at Los Alamos National Laboratory studies this question in the context of asteroid impact preparedness. Her work suggests that humans are actually quite bad at maintaining sustained vigilance for low probability, high consequence events. We either overreact initially and then become complacent, or we dismiss the risks until they materialize. The solution, she argues, is to build systems that don't depend on sustained human vigilance, automated surveys that continuously scan for asteroids, artificial intelligence systems that flag unusual solar activity, protocols that trigger automatically when certain thresholds are met. This transforms vigilance from an active effort requiring constant attention into a passive system that runs in the background and only demands human attention when necessary. In many ways, we're already moving in this direction. The Atlas survey that discovered 3I Atlas is largely automated. Solar observation spacecraft function continuously without direct human control. Warning systems can automatically alert relevant authorities when certain conditions are met. The human role becomes strategic rather than operational, deciding what to look for, how to interpret findings, and how to respond when the automated systems flag something unusual. This is a more sustainable model of vigilance, one that acknowledges human limitations while leveraging our strengths in pattern recognition and decision-making. For 3I Atlas specifically, the balance feels right. We're watching without panicking, we're preparing without overreacting, we're speculating without catastrophizing. If nothing unusual happens, we'll have gained valuable data about interstellar comets and refined our models. If something surprising occurs, we'll be positioned to observe it with unprecedented detail and respond appropriately. This measured approach, skepticism tempered with curiosity, vigilance balanced with rationality, represents mature risk management. It acknowledges that the universe is full of phenomena we don't fully understand, while maintaining confidence in our ability to observe, learn, and adapt. The real danger isn't from 3I Atlas or any particular cosmic object. It's from either becoming so paranoid that we see threats everywhere, or so complacent that we ignore genuine risks. Walking that line requires constant calibration, honest assessment of probabilities, and willingness to update our views as new evidence emerges. As we watch 3I Atlas make its close solar approach, we're practicing this balance. And that practice, that institutional muscle memory of how to approach uncertain but potentially significant events, may prove more valuable than whatever we learn about this particular comet. Let's pull back from the immediate questions about 3I Atlas and consider the broader cosmic context. Because ultimately, what makes this interstellar visitor so captivating isn't just the physics of its solar encounter. It's what it represents about our place in an almost incomprehensibly vast universe. 3I Atlas began its journey long ago, possibly millions or even billions of years before humans existed. It was ejected from a planetary system orbiting a star we may never identify, flung into the interstellar void by gravitational interactions we can only infer. It drifted through the galaxy at tens of kilometers per second, a lonely wanderer in the vast darkness between stars. The distances involved are staggering. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. That's about 40 trillion kilometers, or 25 trillion miles. If 3I Atlas is traveling at 80 kilometers per second, which is roughly its speed relative to the Sun, it would take more than 15,000 years to cover that distance. And Proxima Centauri is our nearest neighbor. The average distance between stars in our region of the galaxy is more like 5 light-years, and many stars are much farther apart. So 3I Atlas has been traveling for an inconceivable amount of time through unimaginable distances, exposed to cosmic rays, bathed in the faint glow of distant stars, following a trajectory determined by gravitational perturbations that occurred when Earth was young or perhaps before Earth even existed. And now, by pure chance, it happens to be passing through our solar system at precisely the moment when an intelligent species has developed the technology to detect it, study it, and wonder about its origins. The probability of this intersection, a specific interstellar comet arriving during the brief window of human technological civilization, is infinitesimally small. Earth has existed for 4.5 billion years. Human civilization capable of detecting interstellar objects has existed for less than a century. The odds that 3i Atlas would arrive during our watch are roughly 1 in 50 million, yet here we are, watching it happen. This isn't because we're special or because the universe arranged this encounter for our benefit. It's simply because there are so many interstellar objects that even infinitesimal probabilities occasionally become reality. This realization is both humbling and oddly comforting. Humbling because it underscores how tiny and brief our existence is against the cosmic backdrop. The galaxy is vast beyond human comprehension, filled with phenomena that dwarf our concerns. 3i Atlas doesn't care that we're watching. It doesn't know we exist. It's simply following the laws of physics, as it has for eons. But it's comforting because it demonstrates that we're part of something larger. The matter that makes up 3i Atlas and the matter that makes up Earth came from the same ultimate source, dying stars that scattered heavy elements across the galaxy. In a real sense, we share a common heritage with this interstellar visitor, even though it formed around a different star. The poet Diane Ackerman wrote, "We are made of star stuff, but we are also made of time." 3i Atlas embodies this truth. Its atoms were forged in stellar furnaces billions of years ago. Its journey through space represents time scales that dwarf human history. Yet for a brief moment as it passes our sun, it intersects with our moment, our now, our technological civilization. Consider what humanity has accomplished in the vanishingly brief time we've been watching the cosmos. We've sent radio signals into space that have now traveled about 100 light years, creating a bubble of human presence that encompasses several thousand stars. But in galactic terms, that bubble is insignificant. The Milky Way is 100,000 light-years across. Our radio signals have barely begun their journey across the galaxy. Yet within that small bubble, within our local cosmic neighborhood, objects like 3i Atlas routinely pass through, carrying with them the chemical signatures of distant stellar systems. They're messengers from parts of the galaxy our signals haven't reached, from stars whose light might not be visible from Earth, from planetary systems that might host their own worlds. This raises profound questions about cosmic interconnectedness. We think of solar systems as isolated islands separated by vast gulfs of space. But the discovery of interstellar objects reveals that material constantly flows between systems. The galaxy is more like an ecosystem than a collection of islands. There's exchange, mixing, interaction, albeit on timescales and distance scales that make human timescales seem fleeting. Some scientists speculate about panspermia, the idea that life might spread between worlds via interstellar objects. Could 3i Atlas be carrying organic molecules or even dormant microbes from another star system? Could Earth have been seeded by an interstellar visitor billions of years ago? There's no evidence for this, and the odds are strongly against it. The harsh conditions of interstellar space, intense radiation, extreme cold, vacuum, are hostile to life. But the possibility can't be entirely dismissed. We know that some Earth organisms can survive in space for extended periods. We know that organic molecules exist in space. The question is whether the full chain, life emerging, organisms surviving, ejection from a planet, enduring millions of years in space, surviving entry into a new planetary system and successfully colonizing, has ever occurred. Even without life, 3i Atlas carries information. Its composition tells us about the chemical conditions around its birth star, Its trajectory tells us about the gravitational environment that ejected it. Its behavior as it interacts with our Sun tells us about physical processes that might be occurring around stars throughout the galaxy. In this sense, 3i Atlas is a scientific treasure, a sample from another stellar system delivered to our doorstep at no cost beyond the effort of observation. We can learn things from studying it that we couldn't learn any other way, not until we develop interstellar travel or receive a message from another civilization. The scale of cosmic loneliness is vast. The nearest potentially habitable exoplanet we've detected is many light years away, requiring thousands of years to reach with current technology. The idea that we might contact another civilization through radio signals requires that such civilizations exist, persist long enough to overlap with us temporally, and happen to be close enough for communication, a chain of coincidences that might be vanishingly rare. But 3i Atlas reminds us that we're not entirely alone. The galaxy is full of wanderers, objects carrying the heritage of distant stars, occasionally visiting our cosmic neighborhood and offering glimpses of the wider universe. They're not alive, not conscious, not trying to communicate. But they're proof that our solar system is part of a larger whole, that we're connected to the galaxy's past and future through these unlikely visitors. As 3i Atlas approaches the Sun, completing a journey that began before recorded history and will end in the depths of space long after human civilization is gone, we get to be witnesses. For a brief, shining moment, our existence and its journey coincide. We get to observe, to measure, to learn, to wonder. That's not terrifying. That's magnificent. Even if 3i Atlas reveals nothing unexpected, even if it passes without incident, simply knowing it exists, knowing that messengers from other stars drift through our solar system, expands our understanding of our place in the cosmos. Before 3i Atlas even reaches its closest approach to the Sun, we've already learned remarkable things. Let's shift our focus from speculation about what might happen to celebrating what has happened. The scientific achievements, the international cooperation, and the expansion of human knowledge that this interstellar visitor has already provided. First, the detection itself represents a triumph. Finding interstellar objects is extraordinarily difficult. They're small, dark, and fast-moving. They appear without warning and disappear just as quickly. The Atlas survey system that discovered 3i Atlas on April 27, 2024, is a network of robotic telescopes specifically designed to scan the entire visible sky every night, searching for transient and moving objects. The fact that we found 3i Atlas months before its solar encounter, giving scientists time to plan observation campaigns, coordinate international efforts, and secure telescope time, is remarkable. With Oumuamua, we discovered it after its closest approach to the Sun, giving us only a brief window to study it before it receded into the outer solar system. With 3i Atlas, we have the luxury of watching its entire inner solar system passage. This advance notice enabled unprecedented preparation. Space agencies repositioned spacecraft to optimize viewing angles. Ground-based observatories coordinated observing schedules to maintain continuous coverage. Amateur astronomers worldwide received information about when and where to observe. The result is that 3i Atlas will be the most comprehensively observed interstellar object in human history. Second, the spectroscopic observations we've already obtained have revealed fascinating details about its composition. Even from Earth, using large telescopes with sensitive spectrographs, astronomers have detected emission lines from vaporizing molecules, water, carbon monoxide, carbon dioxide, methane, ammonia, and several others. But it's the ratios that tell the story. The carbon-to-oxygen ratio is slightly higher than solar system norms, suggesting that 3i Atlas formed in a region richer in carbon. The deuterium-to-hydrogen ratio, a measure of heavy hydrogen, shows slight differences that hint at formation in a colder environment than our outer solar system. These are subtle signals requiring careful analysis, but they're our first glimpses of chemical conditions around another star. Dr. Joanna Schmidt at the University of Leiden led a team that analyzed 3I Atlas's spectrum in multiple wavelengths. Her paper, published in Nature Astronomy, concludes, "The composition of 3I Atlas suggests formation in a planetary system with a different chemical evolution than our own. While the differences are not dramatic, this is clearly a comet, recognizable as such. They provide valuable constraints on planetary formation models and stellar nucleosynthesis." In other words, 3I Atlas is both familiar and foreign. Familiar enough that we can study it using our existing knowledge of comets. Foreign enough that it expands our understanding of what comets can be. Third, the trajectory analysis has been refined to extraordinary precision. By combining observations from multiple sites and using sophisticated orbital dynamics models, astronomers have traced 3I Atlas's path backward through the galaxy. While uncertainties remain, small errors in velocity measurements compound over millions of years, the most likely origin point lies in the direction of the Perseus constellation, roughly 500 to 1,000 light-years away. That means 3I Atlas has been traveling for 15 to 30 million years. During that time, Earth's climate has cycled through ice ages and warm periods. Humans evolved from distant ancestors. 3I Atlas drifted silently through the interstellar medium, occasionally passing near other stars, though never close enough to be captured, gradually making its way toward our solar system. The orbital mechanics calculations also confirm that after its solar encounter, 3I Atlas will be ejected from our solar system with even higher velocity than it arrived. The Sun's gravity will slingshot it back into interstellar space at approximately 90 kilometers per second, sending it on a new trajectory through the galaxy. Billions of years from now, it might visit another planetary system, carrying with it molecules vaporized from our Sun's corona, a cosmic message in a bottle. Fourth, the international cooperation that 3I Atlas has inspired deserves recognition. Astronomers from dozens of countries have collaborated on observation campaigns. Data is being shared openly through established archives. Research papers are being posted as preprints, allowing rapid dissemination of findings. Scientists who normally compete for telescope time and publication priority are working together toward common goals. This cooperation extends to space agencies. NASA, ESA, JAXA, Japan, ISRO, India, and others have coordinated spacecraft observations. The Parker Solar Probe team adjusted their communication schedule to ensure data downlinked during the critical period. Solar Orbiter shifted its observation sequence to prioritize comet tracking. The Chinese National Space Administration contributed observations from their solar monitoring satellites. It's easy to be cynical about international relations, to focus on conflicts and competition. But 3I Atlas reminds us that when faced with cosmic questions, humanity can work together remarkably well. The universe doesn't care about our borders, ideologies, or political systems. A comet from another star visits all of us equally, and studying it benefits everyone. Fifth, and perhaps most importantly, 3I Atlas has energized public interest in astronomy. Social media is filled with discussions about interstellar objects, solar physics, and space weather. Educational institutions are using 3I Atlas as a teaching tool, explaining orbital mechanics, spectroscopy, and plasma physics to students who might not otherwise engage with these topics. Amateur astronomers with backyard telescopes are attempting to image 3I Atlas as it approaches the Sun. While it won't be visible to the naked eye, it's too close to the Sun's glare, dedicated amateur astronomers with proper solar filters and coronagraph attachments might capture images during the closest approach. These citizen scientists are contributing to the scientific endeavor, reporting observations, helping confirm professional findings. This public engagement is valuable beyond its immediate scientific contribution. It creates a population that understands the basics of astronomy, that appreciates the scale of the cosmos, that supports funding for scientific research. When people watch 3i Atlas's passage and learn about interstellar objects, they're building scientific literacy that serves them in evaluating other claims and understanding other phenomena. The transparency of the scientific process around 3i Atlas also builds trust. People can see how scientists work, proposing hypotheses, testing them against observations, revising models when data doesn't fit, acknowledging uncertainties while still drawing conclusions. This demystifies science, showing it as a human endeavor full of creativity, collaboration, and occasional mistakes, rather than a source of absolute proclamations from distant authorities. What we're witnessing with 3i Atlas is science at its best, curiosity-driven, internationally collaborative, transparent, and engaged with public interest. Whether or not the comet reveals anything surprising during its solar passage, this process, the way we've approached it, studied it, and shared what we've learned, represents humanity at its finest. We took a small, cold object from the depths of space and turned it into an opportunity for learning, cooperation, and wonder. We mobilized our technological capabilities, our intellectual resources, and our collective curiosity to understand something that has no practical importance to daily life but enormous significance for understanding our cosmic context. That's worth celebrating, that's worth remembering when the news is filled with conflicts and challenges. Humanity can do remarkable things when we choose to look outward, to ask questions about the universe, to seek understanding rather than advantage. 3i Atlas is giving us data. But more than that, it's giving us hope. Hope that our better instincts can prevail, that our technological capabilities can serve knowledge rather than just power, that we can work together when the scale of the challenge transcends our individual concerns. As we approach the critical moment of the comet's closest solar passage, we do so not with fear, but with anticipation. Whatever happens, we're ready, we're watching, we're learning, and that's exactly what we should be doing. To fully appreciate what we're observing with 3i Atlas, we need to understand how astronomers detect and study objects that are invisible to human eyes. The science of observation is as fascinating as the objects being observed, involving technologies and techniques that seem almost magical in their capability. Start with the fundamental challenge. 3i Atlas is tiny, perhaps 1-3 kilometers across, and it's surrounded by the overwhelming brilliance of the sun during its closest approach. How do you see something so small against something so bright? The answer involves multiple techniques working together. First, wavelength selection. The sun emits light across the electromagnetic spectrum, but its peak emission is in visible wavelengths, the light our eyes evolve to see. Comets, however, emit strongly in specific wavelengths corresponding to the molecules they're vaporizing. By observing at these specific wavelengths, astronomers can filter out most of the sun's light and see the comet's emission clearly. This is where spectroscopy becomes crucial. A spectrograph splits light into its component wavelengths like a prism creating a rainbow. But instead of just seeing colors, astronomers see thousands of individual wavelengths, each telling a story about what molecules or atoms emitted that light. When water vaporizes from 3i Atlas, it produces emission lines at specific wavelengths, 636.3 nanometers for hydrogen alpha, for example. By imaging at exactly that wavelength, astronomers can see the comet's hydrogen emission while blocking out most other light. Different molecules produce different emission line patterns, what astronomers call signatures or fingerprints. Carbon monoxide has its distinctive lines. Methane has others. By analyzing these patterns, scientists can determine not just what molecules are present, but in what quantities, what their temperatures are, how fast they're moving from Doppler shifts, and how they're distributed in the comet's coma. Space-based observatories add another dimension. From above Earth's atmosphere, instruments can observe ultraviolet and X-ray wavelengths that are blocked by our atmosphere. These wavelengths are particularly useful for studying how the solar wind interacts with the comet's vaporized material. When high-energy solar particles collide with cometary molecules, they produce X-ray emission that spacecraft like Solar Orbiter and the Parker Solar Probe can detect. The Parker Solar Probe deserves special mention. Launched in 2018, it's designed to survive closer approaches to the Sun than any previous spacecraft, eventually diving to within 4 million miles of the solar surface. While it won't be at its closest approach during 3I Atlas's passage, it will still be much closer to the Sun than Earth is, providing unique perspectives on the comet-Sun interaction. Parker carries instruments that measure magnetic fields, plasma properties, energetic particles, and electromagnetic waves. As 3I Atlas passes, Parker will detect how the solar wind is perturbed by the comet's presence. It will measure if magnetic field lines are redirected. It will count how many particles are absorbed versus deflected. It will essentially provide a high-resolution scan of the solar environment before, during, and after the comet's passage. The Solar Dynamics Observatory takes a different approach. Orbiting Earth in a geosynchronous orbit that keeps it constantly viewing the Sun, SDO images the Sun every 12 seconds in 10 different wavelengths. Each wavelength reveals different features. Some show the photosphere, the visible surface, others show the chromosphere, the lower atmosphere. Still others show the corona at different temperatures. By combining these images, astronomers create movies showing how the Sun's atmosphere evolves over time. They can track how magnetic field structures form, move, and dissipate. They can see when and where flares begin, how energy propagates through the corona, how CMEs are launched. When 3I Atlas passes, SDO will capture its transit across the Sun's disk, if the geometry is favorable, and will definitely capture any effects on the corona. If the plasma coupling hypothesis has any validity, if there are cascading reconnection events or enhanced coronal heating, SDO will see it. Ground-based solar telescopes add yet more capabilities. The Daniel K. Inouye Solar Telescope in Hawaii, the world's largest solar telescope, can resolve features on the Sun's surface just 20 kilometers across, about the size of a small city. While it can't directly image 3I Atlas, the comet is too small and the Sun too bright, it can detect incredibly subtle changes in the solar atmosphere that might result from the comet's passage. The technique is called differential imaging, comparing detailed observations before and after the event to detect changes. If the comet causes localized heating, density changes, or magnetic field reconfigurations, these high-resolution images should reveal them. Amateur astronomers contribute through a different approach: coronagraphs. These are specialized telescope attachments that create an artificial eclipse, blocking the Sun's bright disk while allowing observation of the fainter corona. Using coronagraphs, amateur astronomers have discovered thousands of comets, most of them sun-grazers that would otherwise be invisible. Some advanced amateurs, equipped with narrow band filters tuned to specific emission lines and coronographic setups, may actually be able to detect 3I Atlas during its closest approach. Their images won't have the resolution or sensitivity of professional instruments, but they'll provide additional data points and demonstrate the democratization of astronomy. Anyone with dedication and appropriate equipment can contribute to scientific knowledge. All of this observational capability has been developed over decades, driven by the desire to understand the Sun and its effects on Earth. 3I Atlas benefits from this infrastructure even though it wasn't built specifically for studying interstellar comets. This is a common pattern in science. Tools developed for one purpose prove invaluable for another. The coordination required to use all these instruments effectively is itself remarkable. Someone has to schedule observations, ensuring different instruments don't interfere with each other while maximizing coverage. Someone has to standardize data formats, so observations from different sources can be combined. Someone has to quickly analyze incoming data to determine if observation plans need to be adjusted. This coordination is being handled by what's called the 3I Atlas Observation Campaign Working Group, an informal collective of scientists from dozens of institutions who meet virtually, share updates, coordinate schedules, and ensure that no critical observation is missed due to lack of communication. The result is that when 3i Atlas makes its closest approach on December 2nd, it will be observed with greater detail across more wavelengths, with better time resolution, and from more perspectives than any previous sun-grazing comet. We'll see not just the comet itself, but its effects on the surrounding space environment with unprecedented clarity. If there's anything unusual to detect, any plasma coupling, any magnetic anomalies, any unexpected chemical signatures, we'll find it. And if the passage is utterly ordinary, confirming our existing models, that's valuable too. Science advances through confirmation as much as surprise, through demonstrating what doesn't happen as much as what does. Either way, the science of detection, this remarkable capability to see the invisible, to measure the unmeasurable, to study an object smaller than a city as it passes through an environment millions of degrees hot, is itself worth celebrating. It represents human ingenuity at its finest, the culmination of centuries of physics, engineering, and collaborative effort. The story of 3i Atlas doesn't end with its solar passage. Whether it reveals surprises or confirms our expectations, it's part of a larger shift in how humanity relates to the cosmos. We're entering an age where interstellar visitors are becoming routine rather than extraordinary. The next generation of survey telescopes will detect interstellar objects regularly, perhaps dozens per year. The Vera C. Rubin Observatory, scheduled to begin operations soon, will survey the entire visible sky every few nights with unprecedented sensitivity. Its computer systems will automatically identify moving objects, calculate their trajectories, and flag anything with unusual characteristics. When an interstellar object is detected, the global astronomical community will receive alerts within hours. Follow-up observations will begin immediately, characterizing the object's composition, size, rotation, and trajectory. If it's on course for a close solar approach, observation campaigns like the one currently focused on 3i Atlas will become almost routine. This raises fascinating questions about resource allocation. If we're detecting multiple interstellar objects annually, how do we decide which ones deserve intensive study? Do we observe them all, spreading resources thin, or focus on the most unusual or scientifically promising? Do we prioritize objects that might answer specific questions, or maintain systematic observations of all visitors? These aren't just academic questions. Telescope time is precious and oversubscribed. Every hour spent observing an interstellar comet is an hour not spent studying distant galaxies, searching for exoplanets, or monitoring variable stars. The astronomical community will need to develop frameworks for making these decisions. One promising approach is the development of rapid response autonomous observation systems. These would use artificial intelligence to assess incoming alerts, compare new objects to existing knowledge, identify unusual characteristics, and automatically prioritize observations. Humans would remain in the decision-making loop for major campaigns, but the initial triage could be handled algorithmically. This is already happening to some extent. The Atlas survey system automatically flags objects with unusual trajectories. The Minor Planet Center's algorithms identify potentially hazardous asteroids. The Transient Name Server alerts astronomers worldwide to supernovae and other stellar explosions within hours of detection. Extending these systems to handle interstellar objects is a natural evolution. But increased detection raises another question. What if we find something truly anomalous, not just a comet with unusual composition, but something that defies natural explanation? Oumuamua sparked this debate. Its elongated shape, unexpected acceleration, and lack of visible outgassing led some researchers to propose exotic explanations, including the possibility of artificial origin. The vast majority of scientists concluded that natural explanations, perhaps an iceberg of hydrogen or unusual venting geometry, were sufficient. But the episode revealed how we'd respond if an interstellar visitor truly seemed artificial, with intense scrutiny, heated debate, and eventually either explanation or acknowledgement of mystery. 3i Atlas, being clearly a comet, doesn't raise these questions, but future interstellar visitors might. As our detection capabilities improve, we might find objects that are harder to categorize, that show characteristics we struggle to explain with current physics, that force us to expand our understanding of what's naturally possible. This connects to the search for extraterrestrial intelligence, SETI. For decades, SETI has focused on detecting radio signals or other electromagnetic transmissions from other civilizations. But what if advanced civilizations communicate or explore using physical objects? What if some interstellar visitors are probes rather than natural debris? Most astronomers view this as extraordinarily unlikely. The default assumption should always favor natural explanations. Space is full of weird natural phenomena, and jumping to aliens whenever something is unusual isn't scientific. But the question of where to draw the line, of what observations would genuinely require consideration of artificial origins, is worth thinking through before we encounter such an object. Closer to current reality, the study of interstellar objects informs our understanding of planetary formation throughout the galaxy. Each visitor carries information about conditions around its birth star. Over time, as we study dozens or hundreds of interstellar objects, we'll build a statistical picture of how planetary systems form and evolve under different conditions. This has profound implications for the search for life beyond Earth. If most planetary systems produce comets with similar compositions to ours, that suggests the chemical ingredients for life, water, organic compounds, various ices, are universal. But if there's wide variation, if some systems produce comets rich in molecules we've never seen, that expands the possibility space for what forms of life might exist. The study of 3i Atlas and its successors also informs mission planning for eventual interstellar exploration. If humanity ever develops the capability for interstellar travel, whether through revolutionary propulsion or generation ships or some technology we haven't conceived, understanding the interstellar environment will be crucial. How common are interstellar objects? What's their typical composition? How hazardous are they to spacecraft traveling at high velocities? Right now, these seem like science fiction concerns, but the history of space exploration shows that what seems impossible in one generation becomes routine in the next. The infrastructure we're building to study interstellar visitors, the detection systems, the rapid response protocols, the international cooperation frameworks, might someday serve humanity's own ventures into interstellar space. More immediately, the experience with 3i Atlas is refining our space weather preparedness. Every solar observation campaign, every effort to model comet-sun interactions, every coordination between space agencies and infrastructure operators strengthens our resilience to solar storms. Whether or not 3i Atlas triggers anything unusual, the process of preparing for its passage makes us better equipped to handle future space weather events. This is the paradox of disaster preparedness. The better prepared you are, the less likely a disaster becomes. By taking potential risks seriously, by developing observation and response capabilities, by practicing coordination and communication, we reduce the probability that any individual event causes catastrophic consequences. The future implications of 3i Atlas extend into education as well. Students currently studying astronomy will grow up in a world where interstellar visitors are routine. Textbooks will need updates. Curricula will incorporate the study of interstellar objects as a standard topic rather than an exotic footnote. The next generation of astronomers will have opportunities to study questions that didn't exist when their professors were students. This rapid evolution of scientific knowledge, where major new categories of objects are discovered within a single career, where the impossible becomes routine within a generation, is both exciting and challenging. It requires flexibility, openness to new ideas, and willingness to update long-held assumptions. It's science at its most dynamic. As we stand on the precipice of 3i Atlas's closest approach, we're also standing at the beginning of a new era in astronomy, an era where the galaxy's diversity visits us directly, where we can study objects from other stellar systems without leaving our solar system, where the space between stars proves to be not empty void, but a populated realm we're only beginning to explore. The implications, scientific, technological, philosophical, will unfold over decades. But they begin here, now, with a small, icy object from beyond our solar system diving toward our sun, watched by thousands of instruments and millions of curious humans, all wondering what secrets it might reveal. As we reach the end of this journey through speculation, science, and cosmic wonder, it's time to say farewell to our interstellar visitor. On December 2nd, 3I Atlas will make its closest approach to our sun, passing within 3.6 million miles of its surface. And then it will be gone, accelerated by the sun's gravity, flung back into the interstellar void from which it came. We'll never see 3I Atlas again. Its trajectory, once it leaves our solar system, will carry it towards some distant, unknown corner of the galaxy. Perhaps in millions or billions of years, it will visit another planetary system, offering them the same opportunity to observe, measure, and wonder that it's given us. But for humanity, this moment, these few months of observation, represents our only chance to study this particular messenger from the stars. What have we learned? If you've stayed with me through all these chapters, through the speculation and the science, the fear and the fascination, you know that the answer is complex. We've learned that 3I Atlas is both familiar and strange, clearly a comet, recognizably similar to objects from our own solar system, yet carrying subtle differences that hint at its exotic origins. We've learned that our sun, despite being humanity's most studied celestial object, still holds mysteries. The possibility, however remote, that an external visitor could influence its behavior reminds us that nature is always more complex than our models capture. We've learned that the galaxy is more connected than we thought, that the space between stars isn't empty but populated with wanderers, that material flows between stellar systems carrying information about distant worlds. Most importantly, we've learned something about ourselves. We've learned that humanity can respond to cosmic mysteries with curiosity rather than fear, with cooperation rather than competition, with transparency rather than secrecy. The way we've approached 3I Atlas with open observation campaigns, public communication, international collaboration, represents our better nature. The title of this video asked if 3I Atlas is doing something terrifying to our sun. Having explored every angle, examined the physics, considered the speculative scenarios, we can now answer definitively, no, it's not doing anything terrifying in any conventional sense. It's not threatening Earth. It's not going to cause civilization-ending solar activity. It's not going to destabilize our star.